It's time for neural networks. Did you guys hear it? Neural networks. Yeah, it's time for neural networks. Oh, come on. Leave me hanging. Neural networks, everybody. It's finally time. We've gotten so much of a grind in to learn everything we need to know, but we're ready for this. We are going to learn about neural networks. All right, and now, before we can learn about neural networks, I'm going to explain every exacting detail of how the brain works down to the last nanometer. We're going to learn this stuff in great detail. Actually not. I'm going to tell you a really sloppy version of this stuff according to a computer scientist who's probably never taken a class on any of this and doesn't really know. But the brain is made up of a bunch of cells called neurons. And neurons have two major interesting properties. One is that they have dendrites that receive signals from other neurons. And the body of the neuron processes all those signals. And when some certain threshold is hit, sends an electrical impulse down an axon, which connects to many thousands, tens of thousands of other neurons. And so, receive signals, hit some threshold or operating point maybe, and then sends out a signal that fires other neurons, and then they'll go around and around in circles, firing each other and somehow creating you and me and us and our ability to have this conversation. And it's totally crazy. It shouldn't work. They send electrochemical signals. And what that means is that there's electric charge somehow that goes, this is the axon. This is kind of like a zoom in on this point where they connect to the next cell. So they'll send an electrical impulse, maybe something like that, some kind of a stimulus. And then there are receptors, and the receptors will receive this signal kind of based maybe on what chemicals, what's going on in the brain. So it might be a very complex relationship between the type of signal that's produced, the timing of the signal, the receptor's current condition, and whether or not that will combine with the signals from thousands of other stimuluses in like a non-time synchronized, asynchronous, blah, 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 to cause the next neuron to fire or to not fire. And in the brain, there are 100 billion neurons, something crazy like that, 100 billion neurons. A really gigantic, staggering number of these tiny cells communicating in this loosely coupled way without a strong central control of what's going on. And that combines to produce a lot of human thought. Like I said, there's 1,000 to 10,000 connections. Each of these branches out to connect to many others, and each neuron's dendrites have connections to many other cells. So it's a highly complicated, very, sparse in the sense of like there's 100 billion things, but there are a lot of connections. Each one is tightly connected. Each neuron is tightly connected into the network that makes up the human brain. Activation time is on order of 10 milliseconds. And what that means is that from the time that this neuron receives enough information to decide to trigger and somehow send a signal down into the rest of the network, it's about 10 milliseconds before this neuron could trigger again or send another signal. And so if you think about it this way, if you were to imagine a stimulus hitting your eye and triggering a neuron in your eyeball, which triggers a neuron in like your frontal cortex or whatever that goes, I don't know, and then triggers another one. And if you were to think that, hey, a path of 100 things, 100 neurons need to trigger based on that stimulus in order for me to decide that, hey, there's a ball coming at my face and I better catch it. Well, 100 neuron chain would take about 1 second from the time the first light hits your eye and starts to simulate it to the time that your brain is saying, ooh, send the signal to my nerves in my hand to try to catch that thing. And the point of that is that it's probably not how it happens, because human reaction time is much faster than 1 second, but it just gives you the sense of how much of the computation that's going on is baked into the parallelism of how the brain works and the connections of that signal fanning out in a distributed way, but then coming together in a very concrete action plan of catch the ball before it hits you in the face in, I think, human reaction time is what, like 50 milliseconds, 100 milliseconds, something along those lines. So 5 or 10 neuron chain with parallelism is what's firing to allow humans to react to the things that they see. Okay, now you know everything about the human brain. Let me teach you about artificial neural networks. And I'm being silly about this because there's a heck of a lot of complexity in the human brain, and there's a heck of a lot of simplicity in an artificial neuron. And artificial neurons are what we have chosen to combine to create the proxy for the human brain and all human processing. And you'll just get a sense of how many corners we're cutting and how far we are from understanding the true properties of what's going on in the human brain and reconstructing that in software. What we're instead doing is being slightly inspired by a vague understanding of what's going on in the human brain and translating that into simple, concrete building blocks that we know how to work with. And we've gotten quite a long ways in machine learning and computer science with this very, very coarse, gross approximation of what's really going on. Now I'm going to go through how in machine learning, neuron has been artificially represented using the tools that we have available to simulate to some degree what one of those single neurons does. And here's the artificial neuron that we're going to use for the rest of this course. We're going to talk about, here we go. And so there are inputs to it which simulate the dendrites in a real neuron. In this case, you'd say there are n inputs to this artificial neuron. Then there's a little building block here which determines, based on those inputs, a simple combination of those inputs, and we'll talk about what that combination is in a second. It produces some form of output, and we call this a sigmoid unit. I think sigmoid is familiar to all of us. It comes from, right? You know where this is going. And then it'll produce, the network, or this neuron produces an output which is proportional to something here. Now let's talk through that. And then this would be potentially the input to the next artificial neuron or something like that, AN something. And now let's go through this. The way that we represent it at the next level of detail is that each input has an associated weight, and you have one weight per input, and then you have this other special input that's always set to 1. That's interesting. And it has a weight associated with it as well. And so what you do to calculate the output of an artificial neuron based on its input is you take each input value and multiply it by its weight, and then you sum it up, and then you pass it through a sigmoid function, and then the result of that sigmoid function is the output of the neuron. It's exactly logistic regression. That's the exact form of the model that we used in our logistic regression learning algorithm. That's exactly what we learned. And it's, not always used exactly in this way. Sometimes artificial neurons don't have this sigmoid thing. They have some other form of a function here, and we'll talk through what's important about that. But this notion of having inputs and weights and a bias weight and summing them and then somehow transforming the linear model that is formed over here into something that is nonlinear for an activation. Now, that's the core of creating artificial neural networks in computer science, in machine learning today. And that's a single neuron, but to create a neural network, we take the features and we input them to a set of artificial neurons instead of sending them just to a single artificial neuron. And we'll get to examples of what this looks like. And then the output of the artificial neurons is used as input to other artificial neurons downstream, and we'll get to examples of what that looks like. And the output of the entire network, at the very end of the network, after the inputs pass to the inputs, pass to the inputs, pass to the whatever, and then you run out of neurons, and whatever gets spit out the back end of the neural network, that's the output, and you use that as a prediction, and we'll get to more details of what that looks like. And even with the gross simplifications that we've made in this, between this artificial neuron and a real neuron, and the complexity of asynchronous interactions and chemical influences and blah, 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 we're still way behind being anywhere near what a brain has to do. In the mid 2010s, we were talking about networks of 50 to 100 layers with 10 to 60 million artificial neurons. Something like 0.5% of what the human brain does. And these were for maybe, competitive with human quality computer vision tasks Now, I know more recently there's these things with billions of neurons that are starting to appear for natural language. So we're making progress in some ways, but we probably are an order of magnitude behind humans just because this is so much simpler than what's going on in the actual human brain. But each of these successful artificial neurons are very task specific for a particular like text understanding or visual understanding or something along those lines. And you could start to imagine that if we as humans brought together dozens or hundreds of artificial neural networks into a conglomeration, and I believe that that's something like what Tesla does, is they've got 30, 40, 50 artificial neural networks that I don't know, have any idea how complex they are, but let's imagine they're in this ballpark. And then you have some simple control system over those that takes the input from all of those and makes decisions. You might be getting to coming up with models that are 10%, 20% as complex in terms of the connections as the human brain is. So maybe we're only 100,000 years away from getting there. I don't know. We got a ways to go. That's the point. They're not going to take our jobs quite yet. Now, let's go through some examples of the structure of a neural network and what taking an image from the Module 3 homework assignment and passing it through a neural network would look like. So here's the 24 by 24 image, normalized grayscale, et cetera, et cetera. And you have a layer of neurons. Remember, it's not just one artificial neuron. So this figure here represents having 4 artificial neurons. Each of them are as equivalent to what was drawn there on the previous slide. So each of them is essentially a logistic regression model. 4 neurons in a hidden layer is the terminology that you would use to describe that. And then you connect each pixel of the input to each of the artificial neurons in this hidden layer. There would be 576 connections to each of these artificial neurons. 500 here, 576 there, 576 there, 576 there. These are essentially like you were doing logistic regression 4 times next to each other. That's the first layer. And you would call the image the values of each individual pixel turn into a feature, and that becomes your input layer is what it's called. So each intensity value is one input, and those create an input layer, goes to the hidden layer, and then after the hidden layer, in the simplest version of a neural network, you are going to have an output from the network, which is going to be your prediction. So you create an output layer, which is another artificial neuron, another logistic regression, type model, and it's going to have one input from each of the artificial neurons in the hidden layer. And again, the bias weight, everything has the bias is everywhere. X0, gonna have a weight for that, and then out of that comes the probability that y equals 1 in a simple case. There's a lot of complexity, a lot of different ways you could do things, but we're just going to build up towards it. Here's your simplest neural network. Now, you should have a pretty good understanding of how to take these weights and pass it through to get the prediction. And so terminology, I'm just going to start using these words over and over a few times. Seem a little redundant, but what we have in this picture is called a fully connected artificial neural network. And that's because every element of the input layer is connected to every element of the hidden layer, which is connected to every element of the output layer. Those connections are complete. Fully connected does not mean that the input layer skips and is connected to the output layer. Things move in order from layer to layer to layer, which is another thing that we humans do that the brain probably doesn't do, but when we're trying to simulate it, we organize things into layers and components and modules, and generally information flows from input through module, output, something along those lines. You would also say for this network that it is a single hidden layer network. It's another important terminology to use. So fully connected, single hidden layer, easy to go. And then we're going to have 2,313 parameters to learn, which are all the weights here and there, and all the weights here, 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 and all the weights there. And so the complexity of this model is 2,313 weights. And what can you do with all that? Well, we've looked at decision boundaries for individual models, for ensembles, and now let's look at it a little bit for neural networks. Remember, we've used this concept before as an example of something that a linear model or a single logistic regression, a single artificial neuron, is unable to capture that concept. The best it can do is something along the lines of what's there in that second image, where you're drawing a plane through the two-dimensional, through the instance space that does its best but doesn't do very well. And so this is similar to a fully connected zero hidden layer neural network, something along those lines. It's just an output layer, and that's exactly equivalent to that. Now here is a decision boundary I learned with 10 nodes in a single hidden layer. And so it's able to represent much more complexity than the individual neurons are able to represent on their own. And is that surprising? Yes, probably. And I'll tell you, without going deep into math or theory or whatever it is, the reason that an artificial neural network is able to represent nonlinear things, even when its components are all linear components and adding up linear components, is that they're not really linear components. You have this activation function, and this puts a nonlinearity between the layers of the artificial neural network. And because of the fact that there is nonlinearity between the layers, you are able to learn nonlinear models even though the building blocks are all linear components. And put that another way is, if you had decided to build an artificial neural network and leave out the sigmoid, you're like, that just sounds confusing. Let's not put any of that kind of garbage in there. It's too much math. I don't like it. Well, this is what you'd be learning with a 10 node, fully connected, single layer artificial neural network. It would be completely linear. It wouldn't be any more powerful than the base units. Nonlinearity, very important to the success and the ability of a neural network to learn complicated structures. So I went and ran with a couple other values just so you could see how adding more structure to the neural network gives you more power to represent more complicated functions. And you might say that this first one here is underfitting. So having 4 hidden nodes, single layer, 4 artificial neurons in the hidden layer, you're not able to represent this concept very well. And in fact, as you go to 6, it's getting pretty good, and then going to 10 and 20 doesn't seem to be doing better. So you might say that somewhere in the 6 or the 10 range would probably be a good trade-off between bias and variance for this simple concept with the amount of noise you have. All right, so now we've seen it conceptually a couple of times. Let's see it with some concrete numbers to try to solidify how the structure of an artificial neural network makes its predictions. Here we have a input with 2 features, x1 and x2, a hidden layer with 2 nodes in the hidden layer, and a single output layer. And so the first thing to do to make a prediction for this sample with this network is you have to figure out what each of these hidden nodes would say. So this first one, x1 equals 1, weight 1 equals -1, so it's -1. Let's go do the bias. So it's 1 times 0.5, so it's 0.5 plus that. And then 0.5 times 1.0 for weight 2 is plus 0.5. So it looks like this guy will get a 0. And then, to come over to the sigmoid function, and a 0 maps to a 0.5, and that'll be a 0.5. Why don't you work through this second one? Think about what values I'm going to draw there and there. Think about that. And let's give it a shot. This one is a 1.0. And then with a 1.0, the activation turns out to be about 0.75. Okay, so we've taken care of the hidden layer. Now we have to figure out what the output layer is going to say. And weight 0 of 0.25. So we have 0.25 plus weight 1 times the activation of the feature in the first position, so that's plus 0.5. Then we have 0.75 times this weight, so it's plus 0.75. And let's click and see what that adds up to. 1.5, math works every time. And pass that through the sigmoid for the output layer, and the probability that y equals 1 is about 82%. So there's a concrete example of working through a neural network, and you could have much more complicated network structures, but the calculation pretty much goes the same way. There's a few types of esoteric things we'll talk about some more as we get into the neural network architectures class, but conceptually, there are a lot of these simple elements and they just pass their information along. And one more time, terminology, it's important to know: input layer. Then you have your hidden layer. Then you have your activations. Every neuron creates an activation, but you could say these two values are the activation of the first hidden layer. And then you have the output layer, and the activation of the output layer is the prediction. That is the logistic regression stacking up interpretation. Let's take a different interpretation. Let's take a computer vision interpretation. Now, think back to the last lecture. If you're skipping around and you jump straight to neural networks, go back and watch that other video. But here we go. We have our input, which is an image of the eye that we're trying to tell if it's open or it's closed. Now we have a hidden layer. And what's in the hidden layer? The hidden layer is a set of weights where there's one weight for each pixel in the input. And those weights taken together can be interpreted as a filter. If you remember back, you could convolve a filter, do a convolution of a filter with an image to find the response of that filter to the image. And if things are lined up, the response would be high. If things weren't lined up, the response could be low or negative, depending on how the filter and the image relate. Well, what we have here is exactly that, except for a network like this, each neuron, artificial neuron, has a number of weights equal to the entire image size. So there's no convolution and sweeping. It's just a single shot. And you get a single value out, which is the direct absolute response, not absolute value, but the actual response of a filter, if you interpret the weights as a filter, to the input, if you interpret the input as an image. As you're learning the neural network, you will learn a set of filters, and you will eventually learn that if a particular filter responds well to the image, you might give it a positive weight and say, hey, when that filter is going on, it's more likely that the eye is closed. And when that filter is going, and when that filter is going on, it's more likely that the eye is open. And then you have like in an ensemble sense, in a stacking sense, you have a model here that takes the inputs of all of those filter responses and says, hey, I'm going to add those up. And in general, my filters were more positive than negative, so I'm going to output a high probability. So in this sense, very simple, but the neural network can learn all those Haar wavelets, all those Gabor filters, all those Sobel stuff, all the handcrafted mumbo jumbo that we were talking about last time, set up correctly, and an artificial neural network can potentially learn versions of that that are specifically focused towards the task that you're trying to do. That's one of the big powers of this type of stuff. There's others, but we'll introduce the powerful concepts slowly as we go. And I just wanted to spend a little time and give you, like I said, we had the logistic regression interpretation, but this is the learning filters and image processing interpretation of what's going on in an artificial neural network. And then to use an artificial neural network like this, what you would do is limited feature engineering. You would take a lot of the computer vision feature engineering and let the network do it. But you would first sort of normalize the input to make it easy for the network to do it. You'd select the right network structure to allow you to do it well. And then the network itself will learn useful features so you don't have to do it by hand. That was the structure of a neural network, but it's not. With all of our other algorithms, that's about how long we talked about the structure. With neural networks, there's a lot more to it. Because so far we've only used a single hidden layer, but you don't have to do that. You could actually slide everything over, slide the output layer over, and stick in another hidden layer. Conceptually, there's no problem with it. And then this is hidden layer number 1, this is hidden layer number 2. Each artificial neuron in hidden layer number n+1 would have an input from each artificial neuron in hidden layer n. And that's a sense of where we call it a fully connected network. And then the output layer would connect to the last hidden layer and take the inputs from the last hidden layer only, and nothing from any of the earlier hidden layers. So again, we'd say fully connected network with 2 hidden layers, and now we have more parameters to learn. It doesn't seem like too many more because most of the parameters are here at the beginning when you have to learn this gigantic mapping from the 24 by 24 image into like something. And then you could imagine that, hey, each of these neurons learns to some degree a useful filter. And then these neurons, what are they doing? They're kind of learning combinations of filters. So this first neuron might have a high weight when this filter and this filter for those two. So when hidden layer number 1, filter 1 and 3 have high activations, then hidden layer number 2, node number 1 tends to have a high activation. We'll get through some of examples of what that might look like, but that's conceptually the way to think about it, is that each layer you add, you can conceptually get more complicated concepts represented by the activation of a single neuron because it's combining the simpler concepts that were upstream. You can also add layers and end up with networks you can't make converge, that take forever to train and are terrible. To reiterate and give another example of this, the filters on filters, you might say that layer 1 would learn the basic shapes of an eye. So maybe this neuron activates when there's kind of like something like that, which would be a corner of an eye. And this guy activates when there's something kind of like that, like maybe an iris is visible. And this activates if there's something that looks like an upper eyelid in the appropriate spot. So those, and of course, they won't learn those concepts directly unless we really train them and try them to. But among this set of neurons in the first layer, they'll learn a palette of the shapes that are relevant to what we're trying to do. Then the neurons in layer 2 will learn how those the palette of shapes combine commonly to create meaningful structures for the prediction that we're trying to make. Now we have 2 layers, a lot more power. We can probably represent more. And that means if we're thinking of the bias variance trade-off, we're going to be able to have less bias, but we're probably going to suffer from more variance. This particular example is not a variance problem per se because we're just, looking at the training set. But I created 2 hidden layers with 4 artificial neurons per layer, and I did a run, and this is how well we were able to learn that concept. And it looks much better than any of the single layer networks. Using 6 artificial neurons per layer with 2 hidden layers looks like that. And then when we go to more, it looks like, what's going on? Well, turns out, and I didn't tune this, I just dropped it into my implementation and ran it. And when there were 20 artificial neurons or 10 artificial neurons per layer with 2 layers, just didn't converge. None of the artificial neurons were able to learn something meaningful. And so the gradient descent or the back propagation that we did just didn't push the weights in a meaningful direction. And essentially, what I believe happened is that the output layer, that single neuron at the end, just did its best. And it came up with these linear things that are similar to what the linear model would have done. Then that one looks like it's the best fit. I just eyeballed it. I didn't do the error bars, but just to show what's going on. All right, so single layer, multiple hidden layers. What else can we do with simple neural networks? Well, we can mess around with the output layer. So far, we've talked about having a single output, and in this case, it's the probability that the eye is opened. But you could have more output layers. You could simultaneously have a neural network that tries to predict if this is an image of a left eye or a right eye, if this is an image of an eye behind glasses, if the person's wearing glasses, or if this is the eye of a child versus an adult. All of these things you could do if you had the labels for it. And what you're doing here is learning a single model that can perform multiple tasks. It's not exactly the same as classification with a lot of label possibilities. It's more like multiple binary classification tasks or probability estimation tasks. And conceptually, what this means is that your y is now a vector. It's not a single value. And we'll get through how loss functions can work with this when we get to that part of the lecture. Conceptually, what you've got is that the hidden nodes learn generally useful filters for interpreting an eye. And once you have however many hidden layers, maybe you have 2 or 3, and they've learned how to understand the structure of an eye, then these output layers can pick and choose from what those layers learned to figure out, well, how do I do my task, which is only really interested in a certain part of the eye or a certain property of the eye, but probably learning these filters in a slightly more generic way than just focusing on a single task would have benefits in terms of avoiding overfitting, which tends to be a problem, and lots of other things. So sometimes taking multiple signals like this and giving them to your network can be better, although we're not going to do this. It's just conceptually something that you can do. And we'll talk through how to do the training algorithms in the presence of this kind of stuff or without this kind of stuff. So now we've gone through the basics of the structure of artificial neural networks. And this slide is to just tell you, this is just really the basics. I mean, these are things that are important to modern artificial neural networks to making them work. And so far we've talked about like this, like just one of them. And each of these topics is pretty darn big. This stuff will get covered when we talk about neural network architectures. These are like advanced modules that you can just plug in to make things work better. This is good for images, to reduce the number of parameters that you need to have before the first hidden layer by actually doing a convolution instead of connecting everything from the input to everything in the layer. Max pooling is about changing the resolution of things in interesting ways. Activation of ReLU is a different form of nonlinearity that is much more efficient and has some other nice properties. Softmax is a way to turn a bunch of outputs into something that's calibrated more like a probability. Recurrent neural networks are ones where the output of the network or the output of certain parts of the network feeds back in when you give the next training sample to the network. It's often used when you're trying to make predictions over series of things. Embeddings we've talked about a fair amount. Sometimes you'll hear these described as bottleneck layers in the network. We'll give some examples of trying to create embeddings in the architectures lecture. Residual networks, a nice structure that's been used to allow people to learn much deeper networks and leverage much more structure without bumping into this non-convergence problem. Batch normalization is a layer that you might add in that fixes skew does normalization in a more fine-grained way. That might be all we say about that. And dropout is a method that you can use to avoid overfitting in neural networks, which is a very important thing. There's often when your dropout means you turn off part of the network when you're learning. We'll talk about that more. Anyway, like I said, we'll explore all of these things in more detail, but just so you know, there's a lot to being good at artificial neural networks. Okay, that's a structure. And that seems like a lot. I don't know how many minutes we are into this, but we're a couple minutes into this thing. Now we're going to get into the loss, and then we're going to get into the optimization. And I must admit that the next couple of slides, there's going to be a lot of math and numbers and indexes to keep straight. Try to go slow. We're going to have multiple levels of examples, but this may be some of the denser slides in the course, but that's okay. Neural networks. Okay, so Mitchell uses mean squared error as the loss. And what that is, here's the, actually this is just the squared error right here. A squared error between y hat and y. And remember that these can be vectors. So what we're talking about here is a single training example's loss. You sum over all of the possible outputs. Remember, you could have eye open, left eye, has glasses, blah, blah, blah. You take the difference in your prediction for that particular output and the true value for that particular output, square it. So that's the squared loss. And then you take the mean of this across your training set. So you add up over every output, over every sample, and take the average, and that's the mean squared error. Now let's go through an example of this. Get out of the way here. Mean squared error loss, and these numbers here come from the first row of this table here. I've been so gracious to create a second row here, which I'm not going to go through, so you can go through it on your own. You're welcome. But the loss here is the y hats are there and the y's are here. So the first output, our y hat is 0.5 and the true y is 1. So we do 0.5 and 1, take the difference and square it. Then the second one, we have 0.1 and 0. We take that difference and we square it. And then we do the 1/2. And what you end up with is a loss of 0.135. Now, if you want to go back and, you're going to say, well, why the 1/2? What does the 1/2 have to do with anything? And if you consider what we're going to do with this mean squared error loss in just a second, so we're going to take its derivative. And so having a 2 there and a 1/2 there, it's a pretty darn convenient thing to do so that we end up with a derivative that's nice and easy to work with. That's just a preview of why that might have been that way. I often think math is just one big game of setting things up so that you can take the derivative easy more than just about anything else. But I'm cynical, I will admit. So, okay, there's a sample of doing mean squared error loss, and you can see y and y hat in this case. This works for regressions. You could use it for probability estimations, I guess, if you'd like to, but it could work generally with regressions. We can also do something called cross entropy or binary cross entropy, maybe in this case. And the BCE, binary cross entropy loss, with a single output reduces to log loss that we use for logistic regression. So you can also use this form of the loss function if you want. And not that we need another example of it, but with multiple outputs. Remember, these two go here, these two end up over there because of this trick for output number 1, for output number 2. And I drew that chart over there in case you don't want to open up your old slide to figure out how that's going to go. And then anyway, so right, these are how you calculate the losses over a single training sample. And then in general, we're going to work with the loss of the entire training set or the loss of the entire test set. And that's how you go from squared error to mean squared error is right here. Okay, so nothing like too complicated in the loss functions. I mean, I guess there's sort of a lot of math in the examples, and working through them, but really it's something we are very familiar with, except a new name because it's been generalized to work with multiple outputs, and mean squared error, which everybody who's done anything is a little bit familiar with at least. And this top one, mean squared error, it's what's in the book. It's what we'll do for our assignment just because Mitchell already worked through all the math for us and we don't have to mess with any of that. Let's just work with his formulas and we'll go with that. All right. Many slides on structure, one slide on loss. Now the backpropagation algorithm. It's a very important algorithm. It's the way to learn artificial neural networks. And you could think of backpropagation as gradient descent over all the parameters in the neural network. That is, for every weight in all of the artificial neurons, what direction should I update them to most reduce the loss of the entire network? Now, it's a little bit more complicated than doing a gradient descent for a single logistic regression. There's all these kind of like intermediate nonlinearities. There's definitely not a convex function that's going to head us straight to a global optimum. We're going to have some troubles with that sort of stuff. But the algorithm is very easy to adapt to all those different neural network structures I talked about. You just do backprop through whatever structure you have. You just have to be able to take a derivative through something. People have worked out all of that stuff. And so it's very easy to figure out how to take the error from the output of the network and propagate it back through the various types of network structures that we might build up our artificial neural networks with. I spoke quickly there, but we're going to go through that in a lot of detail in the next few slides. Like I said, you're going to converge to a local minimum. You won't find the global optimum. It's, unless you have a very, very simple structure and a very simple type of data. Converging is hard. Getting out of local minimum is hard. But you know what? People do it. People apply a lot of data. They've come up with lots and lots of tricks over the last couple of decades. A lot of power, a lot of using GPUs to make things go much more quickly and let you explore a lot more. But backprop can be slow. And training neural networks with a lot of parameters can be slow. And using all the data that you'd want to use to learn very, very powerful neural networks can be very slow. And I just will apologize. This week's assignment, when you implement neural networks, it's going to be slow. It's just going to be a little bit slow. So make sure you don't fall behind in terms of leaving enough time for you to do the tuning that you need to do to complete the assignment. Don't try to program it like the hour before it's due and then think that everything's going to work. Next week, or when, I mean, I know it's not exactly weeks, but whenever you get to the next assignment after implementing the basics of neural networks, we're going to use an open source package that is optimized way more than you're going to optimize, but also you'll be able to use a GPU, assuming you have an NVIDIA GPU and you're willing to install a driver for it. And then you could get things running factors of, I don't know, compared to your implementation, 100 faster with a GPU, 1,000 faster compared to your implementation, 10,000. It's going to be much, much faster. Anyway, there you go. All right, so what is this backprop thing and how does it work? I'm going to go through conceptually, then we're going to go through an example, then we're going to go through probably another, I don't even know everything we're going to do. But first we're going to start off very conceptually. And the steps of backprop with mean squared error as the loss function. Actually, any loss function, but the numbers are going to relate to mean squared error. The first step is called forward propagation. And in forward propagation, you take your sample. Now, you can do backprop one sample at a time, or you can add them up. This example is going to show you how to do it one sample at a time. So you take your sample and you pass it forward through the network. And that means you figure out what each of these artificial neurons is going to say about it, what their activation is going to be. You pass that to your output layer, you get your output, and then you compare it to the true value. So the label, in this case, 1. You predicted 0.82, you were trying to predict 1, so you can calculate the error for this sample. Then the next thing you're going to do is take that error and propagate it from the output layer back towards the hidden layers that contributed to it, and assign to each part of the neural network an estimate of how responsible that part of the network was for the error on this sample. And the way you do that is you calculate the error for the output layer. And so that is essentially related to the loss. That's how much that node contributed to the loss. And since it is right at the end, it's going to have a large contribution to what the problem was. But it's not alone in this. There are two other models, essentially, that are giving it advice, and it's taking that advice and using that advice to make its decision. So you have to say, you think about it like, let's say the output layer very strongly depended on this guy's advice and pretty much completely ignored this guy's advice. What would that look like? If the weight over here was like 100 and the weight over here was 0, you could say that the reason this guy got it wrong was because this guy trusted the wrong person, and because this guy set its weight incorrectly, trusted the wrong part of the network, and also that this part of the network made a mistake, right? Because if the output layer had trusted H2 and H2 had gotten it right, then the output layer would have been doing fine. So there are kind of two mistakes here. And so backprop needs to take that blame and push it back through the network, through every hidden layer, all the layers, everyone, and assign blame. Like, this is how responsible you were for the error that we made on this sample. And now remember, if the sample was totally correct, there wouldn't be much blame, very low blame to go around. And you could say, hey, don't mess with any of the parameters. There wasn't much blame. But if there were big mistakes, then the error is going to get pushed somewhere. And then the third step is, once you've backpropped and attributed the blame, you step each weight to reduce the error that it's contributing to. So if this guy is contributing a lot of error, you want to step its weights a large amount. And that step is going to be exactly equivalent, very similar to what we talked about when we were updating the weights for the logistic regression. That's the concepts. Now let's go through a little bit of where these numbers come from. The blame for the output layer, when you're using mean squared error, you would take the derivative of the mean squared error and end up with something like this. But that's not the derivative of the mean squared error. The problem is there's a little bit more math. And so all of these derivatives get stacked up with a chain rule. We don't need to go through exactly what the chain rule is, but what we're doing is, remember the output, you had the output from the network, which is what this guy wanted to say on his own, but then you pass that through a sigmoid function, right? So we have these two concepts. So to get the actual output of the network, you do the sigmoid function on the output of the linear model at the output node, of the inputs, or you might say, you know, something to do with the parameters. And this is a little bit of a fuzzy sketch, but in order to figure out changes in the parameters, what's the gradient with respect to the changes in the parameters, you need to use the chain rule to unentangle the fact that we're nesting these function calls, the sigmoid, on the output of the network. And that might be just about all I'm going to talk about the chain rule in this entire class. But I will give you one more bit of information, is that to take the derivative of the sigmoid of x, change in the sigmoid of x with respect to the change in x, this is that derivative. And so when you plug this together with the mean squared error, which is the 1/2 y hat squared, take the derivative of that, here's the derivative of that, here's how the chain rule works, plug them together, and you're going to end up with something that looks like that. All we need now is to say, well, the error that we're attributing to the output node is, you know, related to this. When we're using mean squared error, we've done the chain rule, we've done all the derivatives, just take it and use it. Then in order to update the weights of the output layer, which is this weight and this weight, you would say the delta that you would do for the output layer's ith weight is your step size times the error that the output layer made that's attributed to the output layer times the input value. So let's walk through that. So if we're going to do I equals to 1, we're going to talk about, let's do the step related to that. So we're trying to update weight 1, which would be part of this model. We would say the step to do for the output layer's first weight is alpha times the error that it got here, which we can calculate with this thing, times the value of the input, which is the activation that came out of the previous layer. So in that sense, it's the amount that you used the input from that node times the amount of the input from that node. That's the direction that we're going to step, and that's how much we're going to step it. So now we're done with the output layer. That's the update to make there, but now we need to update the weights in the previous layer as well. We need to figure out how much error to attribute to the nodes in the hidden layer. Remember, this is fun. Remember, neural networks. Stay with me. What's the error to associate with this guy? So the error of a hidden layer, so this is H2, so H2 is the activation, that's what OH is, that would be this 0.75. So the activation of that node multiplied by the sum over all of the outputs. Now, in this case, there's just one output because there's only one downstream node from this node that we're trying to compute the error from. If there were another hidden layer here, there might be multiple outputs, or if the network itself had multiple outputs, there'd be multiple values here that you would sum up. But essentially it's saying sum over everyone who used my advice, the amount that they used my advice times the amount of error that they ended up having. So in this case, this value would be this error. So we bring that over there, and this value would be this weight. And that is how you figure out how much to blame this node for the loss made on this particular sample. And then, of course, you have to pass that through the sigmoid function. And that's what that part is for. Okay. I think we'll have more samples of this, so do not despair. And then you would update the weights of this direction's weights based on the, oh, I meant to change this to, this should be an alpha, not whatever that signal is, of the blame here times the value of the input, the size of the input, times the step size. And so that's how you would update the weights here. Then you do the same thing there. Then if there was another hidden layer over here, you could repeat the process and just stack it up, and every blame gets moved downstream, again, like I've said, by the amount of the strength of your statement times the amount that your statement was used times the amount of error that got made downstream. Okay, concept with some math. Now we'll do the exact same thing, but with some numbers, a little bit more numbers. And hopefully this repetition will start to make you see how things click together and it won't seem quite so crazy. I know there's a lot of indexes to keep straight, like, n plus I, O, 1, 7, whatever all these numbers are. It's a bit much, but conceptually it's pretty simple. Let's go through it one more time. So the first step we need to do to take this sample and update these weights in this network using the backprop algorithm. Let's walk through this example. What's step one? Forward propagation. Take the sample, push it all the way through the network, and figure out how close to the true Y does this network get. So we can do the multiplications, weight 0. We've gone through how to do that enough. I'm not going to do that part. We get the activations by passing through the sigmoid function. We come here and we get the output of the network. Now we get the error, and it's 0.18 because the true label was 1 and the network predicted something different. Next step, back propagation. So what do we have to do? Remember, we need to find whatever the delta for the output layer is, and that comes from the thing that we did with the chain rule of the output of the network passed through the sigmoid to get the overall activation. So if you put this value and the 1 into here, you're going to come up with 0.027 as the delta for the output layer. Then you can further propagate. I know in the last example I stopped at that point and did the weight updates, but conceptually back propagate all the way back. So we need to figure out this value right here. And so we would take 0.75 times 1 minus 0.75, so 0.75 times 0.25. Then sum over all of its outputs. It only has one output. We talk about the weight that the downstream person used me with, which would be weight 2. So that's 1.0 times the error downstream. So that would be 0.027. And so we would do multiply, and we would come up with this being about 0.05. Then you could do that again up here. Exercise for the reader, Jeopardy music, but just pause it if you want to do it. But you could calculate that. Then we would update the weights on the output layer. So we would have 0.1 from there times 0.027 times the input, which was 0.75. So this is 0.1 times 0.027 times 0.75. And we could get all those updates right there. And that's the update to the weight here, the weight there, and the weight there. Then we would need to update the weights here. So the delta for the hidden layer, the jth node in the hidden layer for the ith input to that node is let's start with, let's say this bottom one here for x2 related to x2. So we would say this is 0.1 times the error attributed there, which we can bring over from there. So 0.005, and then the input value, which we get from there, 0.5, and that would be the update for weight 2 here. And I'll erase this, but you can do all those multiplications, and you see there smaller weight updates. The weight updates for the output layer were larger, and here they're a little bit smaller because as you're propagating the weights back, they're getting smaller and smaller and smaller. And this leads to one of the problems that you have with the backprop algorithm. It's called vanishing gradients, that the deeper the network is, these gradients get smaller and smaller and smaller. So you're having a hard time updating the weights at the first layer. We'll get to some techniques that help you deal with that. You could do the same thing for this one if you want. Press pause, try to work through these numbers. If you have any questions, please, hit me up, hit up one of the TAs, and there you have it. Now, to bring it together into an end-to-end algorithm, you create the network structure that you want, and you initialize all of the parameters or all the weights to a small random number. Now, there's some formula for this that relates to the number of parameters that you have that's been found to work well. You can also just pick some small numbers. If you want to read up on this, you can. I won't talk about it much more, but if they're all zeros, if all your parameter weights are zeros to begin with, backprop doesn't work. You need to have a little bit of variety so that different parts of the network make different mistakes. Otherwise, everything will be locked to the same mistake and they'll get the same blame propagated back to it, and they'll make the same updates and you won't get anywhere. Then, while it's not time to stop, you repeatedly loop over the training data. In the limit, you could input a single training sample to the network, calculate the output for every neuron, then do the backpropagation algorithm to take the errors from the output and push them into the network. And remember, this is the blame at the output layer, which is the output going through the sigmoid. And then this is the blame at internal layers, which has the activation of that network multiplied by the sum of everyone who counted on you and how much they counted on you. And that, right, the downstream error is this property there. And then this node's effect on the error is that thing I just erased and redrew. So you kind of sum that over every one of your outputs, your effect on the error and the size of the error, and then do this thing for the sigmoid with your activation. Then you update every weight in the network, and the delta is alpha times the blame that you have times the input that was associated with that weight that you're trying to update. And, put another way, the weight at the next step will be the weight at the previous step plus this delta, which right there. One of the tricky things is figuring out what is time to stop. And the reason this is so hard is because the optimization shape is so crazy and there are local optimas everywhere, and you could overfit drastically because the neural network is so powerful. So you can't just work off of the training set per se, and you have to do something a little bit harder, but you don't want to converge too soon, but you don't want to go too far. One thing you could do is say the number of epochs, just say 2, 3, 4, 5, 6. And an epoch is, where I said you take a single training sample into the network. An epoch is you've done all the training samples one time. So you just iterate through all of them once, or we'll see, you might iterate through them in small batches instead of just one at a time. But you go through the entire training set, and then after doing it 5 or 10 or something times, you stop. Another thing you could do is the training set loss, which is not really going to work because you'll start overfitting or whatever. Probably a better thing to do is accuracy on validation data. So here's a sense where you might reserve a large part of your validation data, or you may even have a separate holdout set to decide for any particular neural network run, when do I stop running? And then you'll need a separate set to determine, as I'm trying different hyperparameters, which one of those hyperparameters is better. So you might have to have a holdout set for stopping in addition to the validation set you use for evaluating hyperparameters. And in practice, things can get even a little bit more complicated than this. We're going to talk a little bit about momentum, which is one technique to avoid overfitting. There's also another technique, which is to run a little bit past the point when accuracy on validation data seems to converge, just to be sure, stuff like that. But anyway, this is a simple outline of the backprop algorithm. It's what you're going to need for your homework. It's a good place to start, and there's a lot of details to bump into and enjoy as you keep going. And that's great. That's the algorithm. Let me just go through one more example of how backpropagation would work if you have a hidden layer or multiple output layers. Hide myself so you can see this stuff. But remember, we're trying to get the blame for a particular node, particular neuron in the network. And if we are going to talk about this neuron right here and say, well, where do the components that make up this equation come from? It is the activation of this network. And remember, the same activation will be passed in both of these directions. So post-sigmoid, whatever value this guy says, is this OH11, and that's this component. Then you multiply it by the sum over the outputs, and then we have the weight of the downstream use. So in this case, it's the weight from hidden layer 1 node 1 to hidden layer 2 node 1. And so that's the weight associated with this model on this edge times the error that this person made, plus, remember, we're doing the summation over all the outputs. So we have to then deal with this guy. And so we'd say the weight from hidden layer 1 node 1 to hidden layer 2 node 2, and that's this. So it's the weight from over here, how much this model trusted this input, times the error that got to this level. And so that's just one more example to show you how this stuff generalizes to multiple hidden layers, to slightly more complicated network structures. Now, a couple of details that I want to talk through. One is that I talked about the per sample gradient. And in the past, we had gone through the entire training set and calculated the gradient across all of the samples and then took a single step. Versus this time where I said, well, let's do it one sample at a time. That's how the backprop algorithm was presented there. In practice, you wouldn't necessarily do it one sample at a time. It's common to do what's called a batch. So you would find the gradient on a batch of samples and then take a step. And this batch concept, probably it comes from the notion of doing this on a GPU, where in order to leverage a GPU, you have to move some of your training data onto the GPU along with the model that you're trying to build. So the whole artificial neural network and the training data need to fit there. And so it's very common that you can't fit all your training data because GPUs don't have as much RAM as a CPU does or as your main computer does. So you'd often transfer like 128 samples to the GPU, do all of their backprops in one step, calculate the gradient across all, sum up the gradient across all of them, and then do one step of gradient descent. But let me just give a little quick thought process of, does this matter? What does this mean? Here I've drawn like, if this is where you currently are, and then you have like 1, 2, 3, 4, 5, 6, 7 samples, and you calculate the direction to move the parameters based on each of those, you might get a whole bunch of different crazy directions to go. Every sample might be a different type of a mistake. Okay, so you got all of these competing samples telling you, take a step that way, take a step that way, take a step that way, take a step that way. If you were going to do gradient descent, you would add up all of these recommendations precisely. So you would take this guy's recommendation and that would get you there. Like, here's your starting point. Then you take this guy's recommendation and that gets you over there. Then you take, I don't know what, this guy's recommendation and that pushes you there. Anyway, you just basically sum them up, and then the final point, that's the direction of the gradient across all those samples. It's that direction with that magnitude, and that's the step you take. Fine. Doing it stochastically means that you take some number of the samples, less than all, one or more, something along those lines, and you just do this process on a smaller number of samples. Now, everybody will be telling you similar things. The only thing is that your first step, you may have selected a different guy to trust to take the first step from, and then that'll slightly change the gradient calculation for the next sample. So that might get a little bit off, and then the next sample gets changed and that's a little bit off, and everything is just a little bit off, but it's not really that different, and there's no conceptual reason, I guess, to prefer one over the other in this kind of space. I mean, whatever, everything's a trade-off. And if you compared the step that you would take if you did full gradient descent over every training sample versus stochastic gradient descent, you may end up somewhere like in the ballpark. And who knows with how difficult these optimization problems are, which is actually better. They're very one might be a local optimum, one might not. So there's not a lot of this is really terrible to have to do stochastic versus full gradient descent. And in fact, most of the decision is just based on what you can practically do. What you can fit into RAM at once. Another thing that people tend to do is called momentum. And here it's an example of what a loss surface might look like as you vary the parameters. You start off there and you find the gradient, you step to there, then 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 you get stuck. But you could see that there's a better place to get to. So there's this notion of momentum where you could take the step that you're supposed to take on this iteration or this sample of the stochastic gradient descent, but you also take some beta times the step that you took on the last part of the stochastic gradient descent. And then this can continue adding in there. You kind of like beta should be less than 1 so the momentum doesn't grow, but you keep a history of the previous steps you took, and you also take a little bit of a step in that direction that you were already going, and you build this up over time so that you could potentially take a step, and then the gradient's starting to point back there, but you're like, nah, my momentum's going to get me through, and then you can power through and get past that local optimum, possibly towards something better, maybe towards something worse. It's another set of hyperparameters to tune. Unfortunately, maybe it converges faster if the surface is kind of like smooth. It basically lets you take larger steps. And one more problem, it's the last problem we'll talk about, but it's not the last problem you'll encounter if you decide to spend some of your life with neural networks, is like dead neurons and vanishing gradients. We talked about this a little bit when I was showing you the algorithm, but a neuron can die. And the way it can die is that if the blame that comes to it gets set to 0, then it and things upstream of it are going to be updating their weights by multiplying something by 0, because that's how it goes. And so you can end up in a situation where you will never change anything related to that neuron anymore. And it's not hard to see how that could happen. If the activation of a particular neuron gets close to 0 or 1, if OH is 1, for example, you'd have 1 times 1 minus 1 equals 1 times 0 equals dead, because then your blame would be 0. And once that happens, that's going to always happen, because your activation will never update, because there'll never be any parameter updates upstream of you. And that could be a problem. Maybe not, I might have been a little dramatic about that, but it can definitely cause a serious problem. Another serious problem we saw was as these deltas get propagated from the output layer towards the input layer, they get multiplied and multiplied and multiplied, and they tend to get smaller and smaller and smaller and smaller. So you could be with a network without even very much depth to it, where these blames are not making it all the way up to the input layer. And so you're really never updating the parameters of the first few layers of your neural network. What you're really doing is just passing the input through those first layers as garbage, basically, whatever randomized weight started up there. And then at a certain point that the gradients are large enough, you start optimizing. So you're just sort of using the output side of the network and not using the full power of your network. So those are two big problems. One thing you could do is test to see if it happens, because then you'd at least know, geez, I probably set up the wrong network. I probably have something wrong with my input, that the activations are getting so high that this kind of neuron death is occurring. One way to think about what could cause this is if you initialize your weights crazy, like instead of doing 0.05, you did like negative 500 to positive 500. Another is that you just run the optimization too long, but one that's maybe like more likely for you to bump into is that you don't normalize the input quite right. Here's a way to think about that. Remember, the values in this pixel array are going to range from 0 to 255 if it's a grayscale image. The sigmoid of just 10, like that's right, it could get much higher than 10. The sigmoid of 10 is already 0.9995. You push that through this, and you're already talking about, wow, that gradient's going to vanish a lot. So this is why with neural networks, it's so important to take your input and scrunch it down, normalize it to 0 to 1, but then do the additional steps. I mean, maybe not for the assignments, but do the additional steps of like setting the mean to 0, dividing by the standard deviation, make sure it's well behaved. Sigmoid of 20 is like, the problem grows very, very quickly. You definitely need to be aware of that. Okay, we are getting there. I think by now you should be able to go and implement backprop for simple, fully connected networks with several hidden layers. Do it, get it to converge for some of the problems we're working on. When and how should you think about neural networks? Well, the first way is it's just a model, just like the ones we've been using. In that sense, you could take fully connected networks with a few hidden layers. I've never really got 3 to work myself, but just a couple hidden layers, a small number of nodes, and you have a pretty powerful representation of a model that'd be nice to add to an ensemble, perhaps. Certainly could be competitive with logistic regression, decision trees, probably not competitive with boosted trees if you use some of the more modern boosting techniques. So you probably wouldn't use a neural network where you already have features that you engineered with some other project and you just decided, I'll just use a neural network instead of a decision tree. But another way to use them is that you just do some very simple feature engineering and you let the neural network do the rest of the feature engineering for you by setting up the network structure. So, like we said in the graphical interpretation or in the image interpretation, that you set it up to learn the right filters so that you don't have to do that feature engineering work in the first place. And here you have to be careful to get the right number of parameters so you can actually converge and not overfit drastically. But the discussion in the neural network architectures lecture is going to be about how to deal with these processes. The other thing that you're going to want to do is leverage the recent breakthroughs, understand those architectures, get some GPU acceleration, get a lot of data. You can plumb a lot of data through these, particularly if you have some computing power. And that's, when you start to learn representations of the world, that's where the power of this really starts to unlock. More on this next class. And, right? Neural networks. Wow. There's a lot to talk about. It's a very exciting topic, really a lot to think about. But the quick summary is that they are models that are very crude approximations of the way a human brain works. Maybe that's more marketing than reality, but there you go. It's what we do. Each artificial neuron is a linear model with nonlinear activation. And the nonlinear activation is a very important part of creating the representational power of a neural network. Neural networks are very expressive and they can learn very complicated concepts and they can overfit and they can fail to converge and you can have all sorts of problems. But when they work right, they can be pretty awesome because they can learn features which you might have had to handcraft without them. They might learn what to look for in an image to help you with your task. And then you don't have to go and spend the months or years or whatever it is and get lucky and find that yourself. You let the neural network use the data to find it for you. And there are many, many options for neural network architectures that have been proven in important domains and have shown near human level performance in important tasks. Pretty cool. And the backpropagation algorithm, it's simple, it's flexible, it scales to all the modern neural network structures that we'll get into the future. And it's a little bit technical and you probably are going to want to look at a few of those slides a few more times before you understand it. But when it starts to click in your brain, it's simple and powerful and useful. And I'll see you next time.